So up until now, we've really been focusing on how to analyze a single data set, and now we're going to move into the time domain. And it's clearly easy enough to abstract out everything you've learned and to create your own, list of PFs and loop over them and do the analysis. And this is not much different from that, but the point is that YT already has some very convenient objects to make this less painful with a little bit less hassle, and actually I think to do things in nicer ways. So so the time series data object is an object you get when you do from yt.mods import star. It's just there like load, for example. So you can instantiate a time series data object essentially two ways. It works a little bit different from instantiating other objects by just saying my thing equals this object. Instead we have these methods that lead to instantiating these objects. So we have essentially two ways to instantiate a time series data object. One is with time series data.from file names, and that's where you simply give it a list of all the dataset file names that you want to use. And then the other way is right now a rather Enzo specific way. Enzo, when it writes data, writes out a text log of all the data sets it writes, and if you have that log, you can simply feed it that log, and you can do time series data.from output log and give it that log file. Okay, so now in all of these slides where I use code, the name of the script is up at the top. So if you have the actual repository, this is what I'm referring to every time. So okay, we're going to go back to just using the from file names one for now because it's a little more general. And so we simply use the glob module, which if you're familiar with other languages, glob is just allows you to get a list of things using the star, and it does a couple of other things. But so we get a list of all the files that end in .hierarchy, and then we instantiate our time series with time series.from file names, and we give it that list. And then once you do that, what you should immediately see is that all of these parameter file objects are getting instantiated with all of this output. Okay. I'm going to move a little bit fast through some of these things because it's in the script. We're getting on to more interesting things. Okay. And so this script, time series outputs.py, it's the same as before. You notice in my example here, I have limited the file names to just the first two with this little hard brackets up here, and you can remove that from your example if you want to see them all. And that was just for brevity in these slides. But okay, so when you instantiate this time series data object, what you get is, at least in ts.outputs, if ts is my time series data, we have a list of all the parameter file objects that have been instantiated. So in this script, we can see here down at the bottom, I print ts.outputs, and I can see there they are. And these aren't just strings; these are the actual objects. They've been made with load. Okay. So here's where it gets interesting. Okay. If you remember, all of the data container objects like sphere and region and things like this, they all hang off of the hierarchy object that hangs off of the parameter file. So it's pf.h.sphere, things like that. Well, we still have access to those data containers for a time series object. Okay? So for example, we can create a time series sphere. Okay? So this is done in nearly identical process as to how you instantiate the other sphere. So we have here in this little example here, you can see we do ts.sphere, and then I'm using the max keyword instead of providing an actual center to say center on the max density, and then I'm giving it a 5 megaparsec radius. And this is, as you can see, a little different from how I originally showed you how to instantiate a sphere where I did 5 divided by a unit conversion megaparsecs. However, in reality, you can do a regular sphere in the same way as you can do a time series sphere. You can give it this little list, or actually this is a little tuple with 5 and then the units, like that, okay? So now you have this sphere that is associated, or will be, sort of in a more abstract sense, associated with all of these PFs when you actually want to do something with it. Okay, so let's do something with it. Now we're using time series sphere.pi. Okay, so we instantiate the time series. We created this time series sphere, and now, if you remember, one of the handy things associated with these data containers are these derived quantities, and I'm going to use them in the exact same way that I used the original derived quantities associated with those static spheres, and that's because they are exactly the same thing. Okay, so we can do this. We're going to get the angular momentum vector for the sphere, but in all the PFs. So for all the PFs in the time series data object. Okay, and it's as simple as calling it the same way before, except once we do this, you'll get a lot more printout information in your log. Is this working for people that are trying to do it? Yeah? Okay. You may have to change your path, of course, in the glob line, just because this is the one used to make this actual talk. Okay? And so you can see, then you can print the LVEX, and you can see that you actually have a list of L vectors, of angular momentum vectors for each one. So they're down at the bottom. They're down here. Yeah, I apologize. They didn't quite make it onto the line, but essentially it would return to you just a list that is the exact same size.
So are we sort of moving this sphere through time, or what is going on with this sphere?
So basically what's happening is that for each parameter file object associated with this time series data, we're running this analysis on that, and we're constructing this list that is the same size with the return values for each one of those. Okay, but there is one distinct difference with this. So, all right, you can associate all the data containers with that. So region, sphere, all that stuff. That all works the same way. Okay, but the one distinct difference is that you don't have direct access to the sphere data or the region data. Okay, so you cannot do sphere density and just get all of the values. Okay, that's not going to work, because that would have to give you all the values for all of the spheres, and that just seemed to be too unwieldy, so we chose not to do it that way. So you have at your command some simple canned tasks to go along with these data containers as well. You have these 4 here: slice, plot, data set, current time, years, maximum value, parameter value. And so let's actually show what those are. All these are, they live in a dictionary, much like the derived quantities lived in, sphere dot quantities. These live in time series data dot tasks. Okay. And so here's an example of using the maximum value. Okay. So you can see I can print ts.task.keys, and I can see all of the actual tasks available to me. And now I will do ts.tasks maximum value, and we'll get the density. All right, and then we'll print that. And unfortunately, again, I was one line too long. Sorry about that. But you should have at the end, you should have at your disposal a list of maximum values for all of the PFs contained within this time series object. Okay, is this working for people too? Okay. All right. Here is just another example of using tasks in there. Okay. This is the slice plot data set. So for example, if you want to make a quick movie, all right, just as before we were making some quick plots, well, it's just as easy to make a quick movie, because we actually do want to see how things evolve in time in simulations, right? So we have here a slice plot data set, and it takes these 3 keywords: the center, the field, and then the axis, right? And then you can go ahead and run that, and all you should see is that we're making slices for everyone. And just like that, we've made a quick movie. So movies don't have to be the end-all, be-all of analysis anymore. You can whip one up just as fast as you can whip up a plot. It does each one separately, so it should be pretty non-invasive as far as memory is concerned. Okay, so there are only a few canned analysis routines available at this time. You know, if you're interested in getting involved in developing, this might be a nice place to get your hands dirty, because there are a few, but the good news is making new ones is incredibly simple. So let's do a couple of those. Here's one example. This comes directly from the documentation, so you can follow along there. All we're doing here is we want to know the number of particles of a certain type and the total mass of those particles as a function of time. And I've chosen here for my example, I want to know, for example, what is the number of star particles and what is the total mass in stars as a function of time. You know, in this cosmological simulation that I have, that seems like an obvious thing that one might want to know about a cosmological simulation. So let's walk through how this is actually working, okay, because this isn't as clear as everything else we've done. If we remember before to how we defined fields, you know, our derived fields, we use this thing called a decorator that sat above a function, okay? So we had one that said at derived field. Now we have one that says analysis task, okay? And then in parentheses, what's going to go in here are arguments that will be given in a keyword form to this function. Okay, so we want to know something called particle type. So we only have this one in here for now. All right, I will show another example in just a second that will be far more clear, I think, than this. But then we can see that our function that will be our analysis task takes two things. It takes some object called params, and it takes the PF. So that's the PF, the same PF that we've been talking about all along. So we're going to be handed a parameter file object. We're going to do all the analysis that we already know how to do on it. And this params thing is basically the vehicle for taking in all of these input arguments. Okay, so what do we do inside of this little analysis task? First, we make a data container that's all the data, pf.h.all-data, just like you learned before. Then we have a little bit of NumPy magic, but it's nothing super strange. So this is just getting the particle type. So this would be a field you'd return, right? And then here we're saying if it is equal to the input parameter that we've been asked for. All right, this params.particle type. Okay, this is that argument, right? And then all we're returning is we're returning the sum of all of those. So that is simply the number of them, because this thing here returns a Boolean array that is true, false, for all the ones that satisfy this requirement, right? And then here, we're actually adding up the sum for all of those in there, as you can sort of see how that works, and return it, okay? So then, now that we have our analysis task built, we'll do everything just as we did before, and now that we've done it with this decorator, this analysis task decorator, then we can simply call it the same way we called the other canned ones. So ts.tasks, and then mass and particle type, that's the new one, and we want to look for particle type 2, which in this specific simulation is the particle type for the star particles. Okay, and then we'll just print it out. And once again, I have failed to show anything useful in the space that I was given. All the scripts are here. Yeah, I can run it in the terminal. Why not? They should have it right now, if they've gotten it from the repo. I can, due to time constraints, I will maybe post it at the end. But this should basically just do all this analysis on each PF. Oh, right. Yeah, so this all this is the you can these are the dataset file names that will be used with load. And the reason we're asking for star.hierarchy, you could instantiate a parameter file object with, for example, in Enzo it would be dd000 slash dd0000. Well, I don't know. I might have too many zeros there, but you get the idea. But you could also do it with the dot hierarchy object. So that glob is essentially, you would get the same things out if you did ls and that string. It's just returning a list. Oh, I'm sorry. I've again, I'm just taking the 43rd and 45th, 44th entry in my list. I'm just shortening mine for the example here. Sorry about that. That's my fault. Okay. So we can look at a couple of these. I had so I have my slice here, and what did that turn out? So I ran that, and it looked like this. Okay. And you can see here are all of my, so you could easily smash all this together and make a movie. Okay. That's right. Mm-hmm. That's right. Okay. So that's a nice quick movie in 4 lines. But okay, maybe I don't want to show this to everyone because the color bar moves constantly. So it's not quite as clear and as clean as we'd like it to be. So why don't we write our own analysis task that instead of just making a slice plot, it adds a couple extra things to it. Okay, so let's do that. Okay. All right. Okay, so we're going to make another custom analysis task using this time series custom slice.py. And we start again in the same way. We have this decorator, this analysis task decorator, but this time I want a number of parameters that I want to be able to throw to this function to sort of toggle its operations. Okay, so I want to be able to throw a center, a field, and an axis, which are similar to what we did with the original slice, but I also want to throw my limits, so my z limits. So I'm going to create an additional one, which will be the z limits, right? So all we're saying is, dear function, I will give you this params object, and I will expect params.center, params.field, params.axis, and params.zlim. Is that clear? I'll take that as a yes. So then, here is our function, right? We have params, we have the PF. We make a plot collection. We center it at params.center. We add a slice with params.field and params.axis. And then, now, let's say also we want to, put some of those nice arrows on it for the velocity, all right? We can do that too here. So I'm taking that plot, pc.plots that we just made, and I'm modifying it with the velocity modifier. And then I'm going to set the zlim like we wanted to do. So we'll set it with, assuming that you would want, a list of 2 values, the first and the second. I set it here, and then we save it out, and I'll save it out with a little keyword arrows on there, and use this pf.base name, which is, if it's dd0046, it's called dd0046. Okay? And so we've made that thing. We instantiate our time series object from the file names, and then we run this thing, because now it's in ts.task, just like the others. And we give it all these things that we know that it wants. So we give it a center, a field, an axis, and a limits. And then in the end, what do we get? We get this one. Oh no. It went halfway. Okay. There we go.
So can you go back to the script?
Yeah.
So what you're doing when you add it is up top you're declaring which parameters it can accept, and then you access those as attributes of param, right? And then when you call it, you supply them.
That's right.
Do I have it right?
That's right. That's right. So what did we get in this case? Let's go back to the beginning. Alright, so now we have a constant z-lim, and we have these nice arrows overplotted, and we can go through it. And there again is a movie with a little more customization that we wanted, and again, it's in just a few short lines.